Okay, welcome to lecture here. We're going to hopefully finish up here chapter 13, and then we'll roll over to chapter 14 after that. Okay, so we've been talking about gases and sort of gas laws. We also talked about last time partial pressures. So when we do have a mixture of gases, um, we could calculate what's known as the partial pressures for each of those gases individually. Again, sort of the idea of an ideal gas is, as we also talked about, that there's really no interaction between different gas molecules. So even though we do have a mixture of gases, we could almost assume that they are in that container by themselves. And what that really allows us to do is we can basically use ideal gas law sort of individually for each gas molecule that's present. And then to find the total pressure, we essentially can just add them together. So each of the individual partial pressures added together will give us our total pressure in a gas mixture. And again, we can assume that although they are not really there by themselves, that they are sort of in the container by themselves in terms of the way they're behaving. The nice thing about that is that the volume for every gas in that mixture will be the same. The temperature for every gas in that mixture will also be the same. So essentially, the only difference when you use the ideal gas law and solve for P for each gas individually is essentially the moles of each gas. So you could just figure out the moles of each gas, plug it into the ideal gas law, and then again, get the partial pressures of each one. We also talked about partial pressures when you do collect a gas over water, which is a very common sort of procedure. And in that process of that procedure, basically what happens is, in addition to the gas that you're really interested in, you also collect some water vapor just from the process of doing that reaction in water, basically. So typically, we're not interested in the water vapor, so we do need to sort of subtract it off. So the total pressure in that type of mixture is the pressure of the gas you're interested in plus the water vapor pressure, which is usually found on a table. So the vapor pressure of water is usually sort of a table value. You look it up based on the temperature. And ultimately, what you do is you basically just subtract the total pressure, which in a lab situation would be like the barometer reading, minus the vapor pressure from the table. And that will give you the pressure of sometimes referred to as like your dry gas. And you'll get the partial pressure of the gas you're interested in. Any questions on any of that stuff that we sort of talked about last time? Okay, so where we're left with is pretty much stoichiometry, and we're going to talk really for the remainder here about gas stoichiometry. Um, and gas stoichiometry is essentially done the exact same way as sort of regular stoichiometry problems. The only difference is somewhere along the way, you usually will use the ideal gas law, and we'll talk about that in just a second. But let's first just review something that we did touch upon earlier on in the chapter here, and that's the idea of what's known as STP. So STP again stands for standard temperature and pressure. And when they do say something is at STP, what they're essentially giving you is a temperature of 273 Kelvin and a pressure of 1 atmosphere. So if they say something about STP, like we talked about last time, you literally do have both of these values automatically given to you. And those are the values that you should use. And you can use those in the ideal gas law. So, for example, if we use the ideal gas law here and we solve for volume and put in our values here, 1 mole of a gas, this is our gas constant, and an STP, we would have a temperature of 273 and a pressure of 1 atmosphere. We get this number here. Most people use this number here, 22.414 liters, which we talked about earlier. And what that is with the molar volume of a gas, basically at STP. So that is a conversion factor you could use that we talked about last time. At STP, 1 mole of any gas will equal that volume, that 22.414 liter. Sorry, I got to use that number. It's what's in my head. I've never really seen the rounded version here, but you could technically use, I guess, 22.42 is fine, but 22.414, 22.42, I suppose. It's the same thing. And what this allows you to do, as we talked about a little bit earlier, is especially when it comes to sort of stoichiometry problems, when you are at STP, it sort of gives you a way that you don't necessarily have to use the ideal gas law. So sometimes you could just go straight with this conversion factor and solve for what you're looking for without using the ideal gas law. Now, you could always use the ideal gas law. So you could always put the values in here, our 273, our, you know, 1 atmosphere over here. And you could use it and plug in all the numbers and stuff like that, and you'll get the same answer. So as we talked about last time, sometimes people do want to kind of use this conversion factor everywhere, but only at STP conditions can you use this. So if it is not STP conditions, you do sort of have to use the ideal gas law. And as I mentioned last time, if you want, you can always use the ideal gas law regardless of the conditions. STP conditions, non-STP conditions. So you can always use the ideal gas law and just put the numbers in. But again, this is sort of a shortcut, if you will. Only at STP conditions we could use that sort of conversion. Any questions on that there? So let's really talk about sort of stoichiometry problems that involve gases. And really they are, if they're a basic stoichiometry problem, there's the same 4 steps that we talked about. You want to make sure you have a balanced equation. You want to convert to moles. You want to do your mole to mole relationship. And you then want to convert the moles to some other unit. And I would say probably 9 times out of 10, if you have a stoichiometry problem that involves gases, pretty much these first 3 steps are going to be kind of like a normal problem. You might have something in grams that you need to convert to moles. The difference is at the back end here, a lot of times what you would be looking for, since it is a gas, is say the volume of the gas. And what that means is on the back end of this calculation, instead of using molar mass again, you would use the ideal gas law. And a lot of times you are solving for volume, not 100% of the time, but a lot of times you would be kind of solving for volume at the end. Using the moles that you just did in the stoichiometry part of it. So that's a very common sort of stoichiometry path to do. Kind of everything's pretty much identical to what we've done before, except at the end there you use the ideal gas law. It is potentially possible you need to use the ideal gas law up front. And if you did, it would come here at step number 2. And in that case, you would be solving for N. So N would be PV over RT. So that's a lot rarer sort of situation where you'd probably use it up front, but potentially possible to use it at that point to get to your moles. And then the rest of it would be kind of a normal stoichiometry problem at that. Like I said, probably 9 times out of 10, you're looking the other way. You're going to be using the ideal gas law at the end. So let's take a look at one here and a couple of different ways that, we could kind of approach it here. So for example, if we have a sample of oxygen gas, has a volume of 2.5 liters at STP, how many grams of oxygen gas are present? So there really is a couple of different approaches you could do to this. And it's really, you have 2 options because we're at STP here. Because we're at STP, as I mentioned earlier, the temperature is 273 Kelvin. The pressure is 1 atmosphere. We obviously have a volume of 2.5 liters. So we can definitely use the ideal gas law here, PV equals nRT, and actually solve for N, as that's the only thing we're missing, which would be good because we are looking for grams. So if we solve for N, N would be PV over RT, and everything's actually in the right units. So we would plug it in. We would have 1 atmosphere for our pressure. We would have our volume of 2.5 liters divided by our R, which again is a constant. So you always have this number available to you. And that's that 0.08206 number. And our temperature being 273 Kelvin here. Again, everything's going to cancel out in terms of units, except for our moles. And if we do all that good stuff there, we get 1 times 2.5 divided by 0.8206 divided by 273. That gets us something like 0.111. We'll call it 6L. I'll take it to a few digits here. And these are moles of O2. And at this point, we could convert those moles of O2 into grams by using the molar mass. And if we did that, that is 2 oxygens. So that is 32 grams per mole of O2. And if we times that by 32, we get something like 3.57 grams of O2. So this is one approach that you could take in this problem. You could see, hey, maybe you didn't recognize that you're at STP and you could kind of use a conversion factor instead. You could definitely go right into the ideal gas law and just put the numbers in. The alternative approach is to use that conversion factor that we just talked about. Again, because we're at STP, we know that 1 mole of a gas equals 22.414 liters. And since we already have the volume, we could actually just start with the volume here, and we could go 2.5 liters of O2. Again, 22.414 liters is 1 mole of O2. Again, we could use that because we are at STP conditions. And we could see we do get obviously the same amount of moles, pretty much 0.1115 here. And then if we times it by our 32 grams per mole, we should get pretty much the same answer there, 3.57 grams of O2. So again, you do have a couple of different approaches here, and it's really because we are at STP conditions. And, you know, sometimes people can't remember that conversion or not sure you should use that conversion. And again, what this shows is you could actually, you know, just go right into the ideal gas law. It comes out basically the same way. Any questions on those two approaches there? And as you can see, maybe the bottom one might be a little bit quicker. You don't have to worry about everybody being the right units as the ideal gas law. But again, they both pretty much come out the exact same. Scribble is what we talked about. All right, so let's talk about another one here. We can look at this problem and we have 15 grams of zinc is react with excess hydrochloric acid. That means basically zincs are limiting reagents. So this is a basic stoichiometry problem. We want to make sure first off that essentially the equation is balanced. So that's all good. We have 15 grams of zinc given to us, and we're looking for the volume of hydrogen gas. So this is a gas, so we are looking for the volume. We do have a temperature that is 0 degrees Celsius. We do have a pressure that is 1 atmosphere. So again, this is going to be sort of a basic stoichiometry problem where you could use the ideal gas law at the back end here. And let's see how that would go. So the first step is going to be like a normal stoichiometry problem. We're going to take the 15 grams of zinc and we want to convert it into moles. So zinc is 6539 from the periodic table. And if we do that, we got 15 divided by 60. Try that again. 15 divided by 6539. Going to give us something like 0.22939. Again, I'm just going to take it to a few digits. I'm not rounding so much. That is zinc. And again, this is equivalent to your basic second step in the stoichiometry problem. Third step is to find the two things we're interested in. So one thing is zinc. The other thing is H2. And from the equation, we could see that it is 1 mole of zinc gives us 1 mole of H2. So that's like our stoichiometry part of it. So we could go 0.22939 moles of zinc and do our mole to mole relationship here. 1 mole of zinc from the equation gives us 1 mole of H2. And now we have 0.22939 moles of H2. So when we look at H2, we now have moles. And if we think about the ideal gas law, PV equals nRT, we have the pressure, we have the temperature, we always have R, we now have moles. So we can use the ideal gas law here for kind of our fourth step to figure out the volume. So the volume in this case would equal nRT divided by P. We need to do just one conversion here. We need to add 273 to the Celsius. So that gives us 273 Kelvin. And then we can put our numbers in. This is going to be 0.22939 moles. Our R, which is our 0.08206 liters atmosphere, Kelvin mole. Our temperature, which is 273 Kelvin, and our pressure, which is 1 atmosphere. And if we do all that good stuff there, that is going to get us, call it 5.14. Actually, yeah, 5.134, something like that. Actually, 39. So we would probably go to 4 sig figs based off of this number here, since that was the only number given to us, and that would be liters in this particular case. Question on that. Now, if we look at this, one thing that you might not have noticed, or maybe you did notice, is if we look at our temperature, that is 273 and 1 atmosphere. That is basically STP conditions. And what that means is we essentially can, again, avoid the ideal gas law if you did not want to use it. So we could actually, I guess, eliminate that step right there. And we could have, at this point, where we got the moles of H2, use that conversion, that 0.22939 moles of H2. And again, a mole of H2 would equal our 22.414 liters. And we'll essentially get the same thing with a little bit of rounding, slightly different, but 5.142 basically liters. Essentially the same answer, basically 5.14. Again, if I round it a little bit more strictly through it, we would end up with the same answer. And again, you could have done it this way and avoided the ideal gas law. And the reason you had that second option was because of the STP. Question on that calculation there. All right, so why don't you try one here to make sure. Let's see here. Get all their scribble out of the way, which is everything I scribbled before. Blah, blah, blah. There we go. So why don't you try this one? A sample of oxygen gas has a volume of 2.5 at STP. How many grams of O2 are present? And oxygen is 16 grams per mole. Let me get your question there. Yes. So again, that conversion factor of the 22.414 liters per mole can only be used at STP conditions. So if it's not STP conditions, you cannot do that. So that's what I was saying before. You can definitely use the ideal gas law for any conditions. You could use it for STP conditions, non-STP conditions. You could just put the numbers in and you're good to go, which is sometimes the preference of most people, so they don't worry if they're using it in the wrong situation or not. But if you're confident and you know it's definitely STP conditions, you could go right into that conversion factor. And again, with rounding, you'll pretty much get the same answer. It might be. Did we do this one earlier? We might have. This book problem. Let's just see if we did or not. I think you're right. So I think this one is the one we got. Yeah. So, all right. Textbook examples, that's why they're no good. But we'll just look at them again. Our STP here, because it's STP, as we did earlier, we definitely can go right into that conversion factor. And again, we can use our volume, just like we did earlier there. 22.414 liters is a mole. And that gave us something like 0.11, if I remember right. Yeah, 0.1153. And again, we times it by our 32 grams per mole, and it did come to be. Why don't we try one that we did not do, which would be this one, I think. All right, why don't we try this one here? That one we didn't do, I don't think. 6539 again is zinc's molar mass. Okay, so let's take a look and kind of see the approach here. So we're starting with 2.5 grams of zinc reacts with excess HCl in a single replacement reaction, 25 degrees Celsius and 750 torr. What is the identity and the volume of a gas? So obviously gas is involved here. So that probably should bring up the idea maybe somewhere along the way we're going to need to use PV equals nRT. We do have a temperature of 25 degrees Celsius. We do have a pressure of 750 torr. Um, we are looking for a volume here. So again, if you just start kind of checking off what you got a pressure, you're looking for a volume, R you always have, T you always have. So really the one thing you're kind of missing for the gas is N, which is moles. And that's going to really come from the stoichiometry part. In order to do the stoichiometry part, we got to pretty much do a normal sort of stoichiometry calculation. And pretty much all of those, as we've seen, starts with a balanced equation. So that's really where you want to start here. So basically it tells you you're going to take zinc, which is a solid, and it's going to react with hydrochloric acid and in a single replacement reaction. So if you remember, single replacement, positive, negative guy, this guy has no charge, but when it does have a charge, it's going to be positive. So it's pretty much going to come in and kick out the hydrogen there. And when it kicks out the hydrogen, you are going to produce hydrogen gas. So that would be the identity there of the gas that we're going to produce in this reaction. The zinc will then gain a positive charge, which is +2. The chlorine is -1, which gives you zinc chloride happening over here. Then, of course, none of this stoichiometry works if we don't balance it. So we need like a 2 there. And that might be it. So 2 hydrogens, 2 chlorides, and 1 zinc. So here again is our balanced equation. We want to make sure that we um, get it down correctly and get it balanced correctly, because if we don't get it balanced correctly, then obviously none of the rest of our calculation is going to be any good. The other piece of information we're given is 2.5 grams of zinc. So that's this guy over here. And ultimately, we're not really interested in that guy. We're interested in the only gas that's there, which is, again, the H2. And again, this further tells you it is a stoichiometry problem. So we're going to take what they gave us and convert it into moles. So that's going to be 2.5 grams of zinc using the molar mass from the periodic table, which was 6539 grams per mole of zinc, gets us something like 2.5 divided by 6539, looks like 0.03823. Again, I'm just going to take it to a few digits and not round too much. Now that we have the zinc, we want to go from zinc to H2 because that's the gas we're interested in. And again, from the equation here, not too bad. We see it is a 1 mole of zinc gives us 1 mole of H2. So that makes the math not too bad here. So we're going to have 1 mole of zinc, 1 mole of H2. Again, that's going to cancel the moles of zinc. That's going to leave us 0.03823 moles of H2. Again, hopefully you can kind of see same 3 basic steps here. Balance equation, convert to moles, mole to mole relationship. So what's left now is to figure out the volume. And you may be tempted to go, cool, I got it in moles. Let me just use my 1 mole is 22.414 liters. And if you use that here, it would be wrong. And that is because when we look at the temperature here is not 273. It's actually 298 Kelvin when you add it, which means it's not STP conditions. And also our pressure here, which is 750 torr. If we convert that to atmospheres, that is 750 divided by 760 actually gives us something like 0.987 atmospheres. Also not 1 atmosphere. So we are not at STP in this problem, which means we cannot use that conversion. So that leaves us only really one option, which is you have to use the ideal gas law here basically to solve this problem. Any questions on that there? So we do need to use PV equals nRT. And because we are using PV equals nRT, we need to make sure everybody's in the right units. So I just did a couple conversions, which puts everybody in the right unit. We have our temperature now in Kelvin. We do need to convert our pressure into atmospheres, and everything else should be okay at that point. So we're going to solve for V. V would be nRT divided by P. And if we put that numbers in, we have our 0.03823, our R, which is a constant, and our temperature here again is going to be 298 Kelvin, all divided by our pressure, which was about 0.987 atmospheres. So if we punch all that in, let's see here. Take that 0.08206 times 298 divided by 0.987. It's going to give us a volume of about 0.947 liters, or about 947 milliliters. Again, the moles will cancel, Kelvin will cancel, atmospheres will cancel, leaves us just liters that's left. Any question on any of those steps there? And again, this is really where it sort of varies from a normal stoichiometry problem in most cases with gases is, as you can see, very, very common. Step number 4, you kind of use ideal gas law. Any questions on any of those steps, where any numbers came from or anything like that? Okay, if there's none, then why don't you try one more here just to see what you come up with. So we have 4.55 grams of NH3 is reacted with HCl to produce ammonium chloride. What is the theoretical volume in liters of the gas if the reaction is carried out at 25 degrees Celsius and 1.05 atmospheres? Nitrogen is 1401 and hydrogen is 1.008. All right, take a couple minutes to see what you come up with. Okay, so let's take a look and see. Um, so again, we're reacting NH3 with HCl to produce ammonium chloride. So we are going to need an equation here. So it pretty much tells us, so we got NH3 plus some HCl going to make some ammonium chloride, which looks something like this. We want to make sure it's balanced, and it looks like it should be. So we got one nitrogen on both sides, also four hydrogens, and one Cl on both sides. In this particular case, we are starting with 4.55 grams of NH3 and also 6.43 grams of HCl. And we want to know pretty much the volume here of our ammonium chloride. We also have a temperature given to us, which is 25 degrees Celsius, which is the same as 298 Kelvin. And we have a pressure of 1.05 atmospheres. That pressure temperature relationship tells us we are not at STP. So again, we cannot use that conversion that we saw before. We are going to have to use the ideal gas law here, PV equals nRT, at some point to figure out the volume. Now, we do have our equation. The next thing we want to do is convert to moles, but you may also notice something else that we've seen before when we've done stoichiometry, and that is I have the starting amount of NH3. I also have the starting amount of HCl. I pretty much have enough information to figure out the moles of each of those. And that means that this, in addition to being a gas stoichiometry problem, is also a limiting reagent problem like we saw before. So you do need to figure out the limiting reagent and also take that into account because that's going to be the one that produces the amount of product that we're going to make here. Any questions on that so far? All right, so trying to remember how we did it here. So we did it this way, I think. So in our method that we chose to do it was basically just do two separate calculations basically to figure out how much product we're going to make from each of them. And the one that makes the least amount of product should be your limiting reagent. So I think that was the method we chose. So we will do that method here first for NH3. And if we do NH3, we're first going to convert it into moles. So we're going to take the grams of NH3. We're going to use the molar mass from the periodic table for NH3. So that is 3 hydrogens at 1.008 plus 1 nitrogen at 14 gives us 1703 grams per mole of NH3. And if we do that, 4.55 divided by 1703 gets us something like, if you got a number here, 0.2672 moles of NH3. We're not interested in NH3. We're interested in our product here. Again, it won't always be one-to-one relationship, so make sure you do balance the equation. So we'll do the 1 mole of NH3 gives us 1 mole of our ammonium chloride, and we'll just assume, I guess, that it's a gas, 0.2672 moles of ammonium chloride in this particular case. Again, the basic steps here are still the same: balance equation, convert to moles, and mole to mole relationship. Here, though, because we just talked about we're not at STP, we are forced to obviously go only through the ideal gas law. And here we're going to solve for volume, and it would be nRT divided by P. I did the one conversion we needed, which was to convert our temperature into Kelvin. Everybody else should be okay at that point. So 0.2672 moles. As I'm going to run out of room here, 0.08206. I'll just go above times 298 Kelvin, all divided by our pressure there, which was 1.05 atmospheres. And that will get us 0.08206 times 298 divided by 1.05 gets us something like a volume of 6.22 liters produced here from NH3. First off, any questions on that part of the calculation? So because it is limiting reagent, we're pretty much going to do the identical calculation here but we're going to start with the 6.43 grams of the HCl. And let's do that then. So I got another spot to write. Perfect. So this was 6.43 grams of HCl. We're again going to convert it into moles using the molar mass. So it's 1.008 plus a 3545 for our chlorine gives us 3646. And that gets us 0.1764 moles of HCl. Again, from the equation, it is still a one-to-one relationship between the HCl and the ammonium chloride. So 1 mole of HCl, 1 mole of ammonium chloride, again, from the equation, gives us 0.1764 moles of HCl and moles of ammonium chloride. At this point, we then can go into our ideal gas law, solving for V like we did previously. The only main difference here will be our moles, so 0.1764, 0.08206. Our temperature, which was 298, and our pressure still 1.05 atmospheres. And that will get us 4.11 liters. And in this particular case, again, the one that produces the smaller amount, which in our case was the HCl. HCl would be our limiting reagent, and this should be the amount of H2, or the theoretical yield that we would produce. Any questions on that calculation there? So again, you can see in this stoichiometry calculation, it can be a limiting reagent problem. You basically handle it the same way as a normal limiting reagent problem. Again, just somewhere along the way, you're going to be using that ideal gas law. Any questions on gas stoichiometry, gas laws in general? Any questions on any of that? Okay, so that should wrap up this chapter. We will then roll into chapter 4. Just give me a second to go grab that there. Okay, so we're off to chapter 4 here, and we're going to talk about liquids mainly, not too much solids probably. We're going to talk about some intermolecular forces that happen between liquids. We'll also talk about boiling, freezing, melting, all that. Yeah. Yes, so experiments 17 and 18 are pretty much based off of gases, which we just finished. So gases and kind of the stoichiometry part that we just talked about as well. So we should be in good shape on 17 and 18 on that, I think. Other questions? Okay. All right, so let's talk a little bit about our liquids and solids, maybe, if I get through. There we go. So first, talk a little bit about water and its phases, and the sort of the differences between gases and solids. As we've talked about before, when we do get to sort of the gas phase, we're at a point where everybody is pretty much sort of completely broken apart from one another. They're flying around freely from each other. That obviously is what causes the pressure that we associate with gases. They also really fill the container pretty much completely and uniformly as they are moving around in there, as we can see in this nice picture here. They are very compressible. Again, we can compress gases, also increases the pressure that we associate with it as well. Obviously, when you compress a gas, the volume gets smaller, the gas molecules get closer, and obviously there's a lot more collisions that occur, and obviously that increases the pressure in most cases. Now, different, right, is solids, as we'll talk a little bit about towards the end of this chapter, but basically the solid state, right, everybody, as you can see here, is usually fairly packed in pretty tight to one another. There's not a lot of room for movement. They don't have enough energy really to kind of pass each other or anything like that. And that's why in most cases, solids are usually a lot more dense than, say, the liquid state or the gas state, because they are pretty much packed in there relatively tight to each other. They usually have a very rigid type shape because of the way they're packed in. And ionic solids, for example, when they do sort of come together in the solid state, they come together in a very, very ordered sort of situation. It's such an ordered pattern that you pretty much could take just a snapshot, little piece of a sort of solid crystal. And there's enough sort of repeatable order that you can almost rebuild the entire structure just from a very small sort of pattern of it. And again, that's because it's very, very sort of repeatable, has long range order when we talk about ionic solids. Liquids, on the other hand, which is in the middle, obviously, as we've also talked about, usually fairly packed in pretty tight to each other, but there definitely is a lot more room for movement. And that's why when we think about liquids, right, we think about them as terms of being fluid and being able to kind of flow and stuff like that. Again, they have enough sort of energy to sort of move past each other, which gives it that sort of fluidity. One notable exception to sort of the normal states of matter, in terms of how we think about it, is water. Water, right, is actually less dense in its solid state than its liquid state. And that's an unusual sort of property that happens with water. And as we'll talk about it a little bit here in this chapter as well. But essentially, what happens when water goes into the solid state and all these waters pretty much get together is, as they sort of bond to each other in this sort of state, what ends up happening is it creates a lot of really open areas or volumes between the different water molecules. So when it comes together sort of in that solid state, it really doesn't pack super tight to each other. It creates a lot of open spaces between them. And basically what happens is you get this bigger volume. If you just think about density, which is mass divided by volume, because you got all this extra empty space, this number gets bigger, and that means that the density goes down and is smaller. So again, unusual sort of characteristic water has, and it has to do a lot with what we're going to talk about here in this chapter as well, which is hydrogen bonding and how it sort of comes together. But most things is usually more dense in its solid state. This is a heating and cooling curve, and a couple of things. These are where we see these transitions. So this is basically solid. This is basically liquid. And this is basically gas over here. And the transition of these things happen at the normal freezing point or melting point, or the normal boiling point, um, in terms of going from liquid to gas. So when we're going from solid to liquid, our liquid back to solid, that actually does occur at the same temperature. So for something like water, that's 0 degrees Celsius for something like water. And at exactly 0 degrees Celsius, as you can kind of see right here on the chart, it is pretty much plateaued, which means at exactly 0 degrees Celsius, you are in pretty much equilibrium, is known, between the two states. And what that means is at exactly 0 degrees Celsius, you pretty much have some solid and you have some liquid happening at the same time, kind of like ice crystals, if you want to think about it that way. It's really not until you get above 0 degrees a little bit that you're into liquid water. And it's not until you get a little bit below 0 degrees that you're actually sort of into solid or ice in the case of water at that point. It just depends on what you're going to do in terms of energy. So if we continue on an endothermic process, which means that we're going to put heat and energy in, we will continue the process of going from solid to liquid. All of our solid guys will gain enough energy to basically melt and go into the liquid phase. If we go more of an exothermic pathway at that point, we would actually be going from liquid back to solid. And exothermic means, again, heat and energy is going to be released. So as those liquid molecules lose that energy, what ends up happening is they, again, no longer have enough energy to kind of pass each other anymore. And they basically come into the solid phase at that point. And right dead on at 0 degrees Celsius, that is where we have basically both things happening. As we'll see a little bit later on in this chapter as well, there's actually a specific amount of heat required to do a transition of just that, just simply taking something, say like water, in the solid state to the liquid state and back, and not change the temperature. So again, that occurs at 0 degrees Celsius. That is what is known as the delta H of fusion, or the heat of fusion is what this is. If you remember, we saw delta H earlier on in the semester when we talked about energy. The heat of fusion is what this is sometimes referred to, is really the energy required to take a substance from the solid state to the liquid state, not change the temperature, but just change the state. So take ice at 0 degrees Celsius to liquid water, basically at 0 degrees Celsius. And if you remember as well, we talked about delta H and exothermic and endothermic. If the delta H is a positive number, it's endothermic. If the delta H is a negative number, it is exothermic. Now, the same thing happens when we do get to this transition here. This is our transition of going really from liquid to gas or backwards. So going from liquid to gas or gas back to liquid. This also occurs at the same temperature, and that is the normal boiling point for a substance. So for something like water, that's 100 degrees Celsius for water. And just like at 0 degrees Celsius, at 100 degrees Celsius, you also have both of those phases happening at once. So at exactly 100 degrees Celsius, where this line is kind of just flattened, so I drew over it, you basically have liquid and gas sort of happening at the same time. Not until you get above 100 degrees Celsius, for example, for water, that you actually would get to water vapor or gas or steam or whatever you want to call it. It's not until you get a little bit below 100 degrees Celsius that you would actually have liquid water. So exactly at that temperature, you have that sort of process. And it's the same sort of process as below as to what is happening. If we are going from liquid to gas, that is going to be an endothermic process. If we put heat and energy in, our liquid molecule is going to gain enough energy basically to break apart from each other and go into the gas phase. And vice versa, if we're going from gas back to liquid, that again is a more exothermic process. Delta H would be negative. And at that point, when those gas molecules are flying around and they lose energy, they're basically going to slow down. And as they slow down, they're going to kind of clump together, if you will, and fall into the liquid as they, again, don't have enough energy basically to pass one another. And doing that transition, going from, say, water in the liquid state to water in the gas state both ways, there's also a certain amount of energy required just to do that. And as we will see, that is what is known as a delta H of vaporization. The heat of vaporization is referred to. And that is the energy required to take a substance from the liquid state to the gas state. Again, not changing the temperature, just solely changing the state of the substance, or backwards, going from gas back to liquid. Again, for water at 100 degrees Celsius, that is where that would occur. The amount of energy required to do these transitions is different. And you can just see it in sort of the lines here. When we look at the comparison of this line here, going from solid to liquid, to how big this line is over here going from liquid to gas. It takes a lot more energy to do this transition than it does going from solid to liquid. And that is because as you go from solid to liquid, in the solid state, everybody's pretty tight to each other. In the liquid state, they're still relatively close to each other. But when you do the transition of going from the liquid state to the gas state, in the liquid state, they're pretty tight to each other, but in the gas state, they have now completely broken apart from each other. So it takes a lot more energy to do that. Just for reference sake, and we might see similar to this number, for water, approximately it's about 333 joules per gram is the delta H of fusion for water. And that is the transition or the energy required to go from solid to liquid. In comparison, the delta H of vaporization for water is about 2260 joules per gram. So something like 7 times as much energy is needed to convert a gram of water from liquid to gas than it is to go from solid to liquid, or backwards, going the opposite way. These numbers would be the same number regardless of which way you're going. So if we were going from solid to liquid, that's endothermic. So it would be positive 333 joules per gram. If we were going from liquid to solid, that is exothermic, it would be negative 333 joules per gram. Same deal over here. Liquid to gas is endothermic, it would be positive 2260 joules per gram and negative 2260 joules per gram going the opposite direction, going from gas back to liquid. So the energy, the heat of fusion, heat of vaporization is really the same number regardless sort of which way you're going. Just like we talked about when we talked about sort of specific heat and all that and energy, it's really just a sign that basically varies and stuff like that. Any questions on that there? Okay. So I think everything I just scribbled is everything that's going to come up here, I think. All right. So when we look at a heating or cooling curve like this, and we want to really sort of figure out the heat or energy that's happening as things are transitioning, we do also come back to, as we will see, our equation that we saw before, which is our specific heat equation. And if you remember the specific heat equation from earlier, Q is our heat or energy, M is the mass, S is the specific heat capacity, and delta T is our change in temperature, which is our final temperature minus our initial temperature. So as we talked about when we did this, this is the important part. This is really the part that makes it either positive or negative. So when we look at sort of these different parts of this curve, there's different sort of calculations that you typically would do. Specific heat, we use the specific heat equation we use when we are changing the temperature, but this phase stays the same. So what that means is we're changing the temperature, but our substance remains, say, liquid all the way through that change. Our substance remains solid all the way through that change, or, gas all the way through that change. When we keep the same temperature, but change the phase, this is where we want to use something like the delta H of fusion or like the delta H of vaporization. So what does that mean when you kind of graphically draw it on a curve like this? Anywhere on a curve where you see it kind of go up, you should be using Q equals ms delta T. So anywhere from, say, here to here, if you needed to do a calculation, that should be your specific heat calculation. Anywhere from here to here, all that is liquid all the way through there. That is also a specific heat calculation. Anywhere from here to here, also a specific heat calculation. The places where you would not do that is essentially what we were just talking about and just looking at, which is essentially number 2 on this chart, this kind of squared part here, that plateaued part, and number 4 here on this chart. So for number 2, you would use the heat of fusion. For the number 4 transition, again, the temperature is not changing, but the state is changing. You would use the heat of vaporization. So sometimes when you get a problem, and we'll see a problem, I think, coming up as well, where you want to do that calculation. Sometimes it's good to kind of draw it so you don't miss any of those sort of transitions, and it will allow you to sort of figure out certain things. As we'll see in just a second as well, when you use a specific heat equation, you do want to be careful of the specific heat capacity. The specific heat capacity for substances does change depending on the state. So when you go look it up in a table, you want to make sure that you actually get the specific heat capacity for, say, water in its liquid state, which is that 4.184 number. Water in its solid state or gas state is more like 2 point something number. So they are different depending on the state. So you want to make sure that you not only look up what you are looking for in terms of a substance, but you do look it up in terms of the right phase that it's in. Otherwise, again, you'll get the wrong answer. By the way, if we want to know how much heat to take something from like here all the way up to here, we basically would just add up all the individual energy needed to do each step. So for example, let's just say there was 5 steps to go. You would add up all 5 numbers. That would give you the total amount of heat and energy required to do that. Any questions on that there? And we'll see an example of that in just a second. I think in this chapter, we'll get to one. All right. So let's talk a little bit about some of these things. During the process of melting of ice by adding heat, which is an endothermic process, what would happen to the temperature of ice? So again, remember that pretty much whenever you change a phase, go from solid to liquid or liquid to gas, those guys happen on those curves at those flat lines. And the flat line represents, if you go to the y-axis here, a constant temperature. So these things happen at constant temperatures. So again, for water, 0 degrees Celsius, that's where we would see melting occur. For water, boiling would occur at 100 degrees Celsius. Again, those transitions occur at the same temperature and it remains constant regardless of which way you're going. So which are stronger, intramolecular forces or intermolecular forces? And we're going to talk about some of the differences between those. But just to give you an idea, again, of what these mean, intramolecular force means within the molecule. So that is the force that holds an individual molecule basically together. An intermolecular force is a force that holds 2 molecules together. So if we just take, for example, water, just one individual water molecule here, the covalent bond between the oxygen and the hydrogen on the left and the oxygen and the hydrogen on the right, these are intramolecular forces. And that is the covalent bond, basically. Again, between the oxygen and the hydrogen, they're sharing electrons. When we get multiple waters together, as we will see shortly in this chapter as well, when we get these multiple waters together, water is a polar molecule and it's more positive on the hydrogens, more negative on the oxygens. So when they get together, what ends up happening is the oxygen in one, which is negative, is attracted to the positive hydrogen in the other. And as we'll see in this chapter, that is what is known as hydrogen bonding. And that bond that holds that one entire water molecule together with this other entire water molecule, this is what is known as an intermolecular force. So intramolecular force within a molecule, so like covalent bonding, for ionic bonding, that is intramolecular force. So when you have an ionic bond in that electrostatic attraction, which is that fancy positive negative attraction, that is an intramolecular force. That is a super strong intramolecular force that happens. So how do we know that, the intermolecular force is weaker than the intramolecular force? Well, we could probably have a very simple explanation of that. Most people have probably boiled water at some point. And when you boil water at some point, if you haven't, give it a try. But if you have done it before, what you see is as you boil the water and you heat up the water and it starts to boil, the first bond that breaks is this bond here, the bond between two water molecules, because then what you get is H2O in the gas phase, right? It's a steam. You get H2O in the gas phase. We know that's what occurs when you heat water, because if the opposite was true and the intramolecular force was weaker, what would happen is as you would start to heat the water, you would start breaking these bonds, which is probably not a good thing because that's going to generate hydrogen gas and oxygen gas. And if that did happen, I imagine if you're trying to make pasta, you probably want to get to the pasta part at that point, and bad things would happen. So this definitely doesn't happen when we heat water. What happens is actually down here, which tells us that the intermolecular force is always weaker than the intramolecular force. So in terms of this question, which one is stronger? The stronger one is always the force that holds an individual compound together versus the force that holds multiple molecules together. Any questions on that? Okay, we will lay it up there for today for lecture. Like I said before, we're going to do we'll watch the two videos today,